welcome to our speaker, Professor N.P. Singh, sir. We are delighted to have your presence in our STC. Thank you, sir, for providing a valuable time for this STC. I am going to introduce about our research person. Professor N.P. Singh has 16 plus years teaching and research experience. His research, uh, his current research interest is machine learning, wireless sensor network, and security IoT. He has handled many government projects like ISEA project, phase second, DIT, GOI as principal investigator, nodal officer for implementing NKN project, DIT, Government of India, ENICT academic DIT, GOI as co-principal investigator, research projects of DRDO, etc. He has published more than 40 research papers in ACI Scopus Journal and more than 90 papers in international conferences. He has organized more than 25 workshops on cutting-edge technology. 10 PhD scholars has completed his PhD under his supervision. Currently, 25 scholars are working under him on different research issues related to MLDL, few short learning, wireless network and security. He has guided 35 MTech theses. He is reviewer of many journals of IEEE, SCM, Springer. He is active member of many international national professional bodies like senior member of IEEE, senior member of ACM, CSI, fellow of IEI, life member of Indian Society for Technical Education, IST, etc. He has many administrative responsibilities like HOD, Associate in Academics, Professor in Charge Computer Center, etc. Welcome to you, sir. Hand it over to you, sir. Please.
Thank you, Dr. Dilip. Thanks for giving me this opportunity to give my talk. Rather, it is kind of a discussion with the learned people. I will share my presentation. I hope it is. Are you able to see this, my screen?
Yes, sir. Your voice is
No,
audible.
sir.
Slide is not visible right
PPT is visible?
now. PPT is
No,
not
sir.
visible.
Okay, just a minute, just a minute, just a minute. Now,
Yes,
Yes,
sir.
visible.
okay, thank you. So today, in this session, I will be talking about the machine learning, the new paradigm. As you can see, the few shot learning, and that to be we will be discussing in the medical domain. I hope most of the people is aware of the machine learning and different algorithms and the different terminology that we used to have in our machine learning and in fact in the deep learning and so on. So this could be my outline of today's presentation. Background, it is required to understand the need of the some different innovation in the machine learning, and that is what our few shot learning. And little bit we will discuss about few shot learning. There's some theoretical knowledge about few shot learning because that will help you to understand that how the few shot learning is important and how do we use this technique or this algorithm, especially in case of the medical imaging. As you are aware of, this medical imaging is a little bit complex analysis compared to other objects. Then some of the experimental results we will try to do the analysis, specifically in terms of the generalization, because the the very fundamental concept of the machine learning is not that it should be depending on the data set. I mean to say, if you have developed some model for machine learning and you have done some experiment on some particular data set, it does not mean that the performance of your model will degrade the moment you are using some new data set or some new inputs. So we have to try very hard to achieve the goal of the generalization in the machine learning, which is actually a real tough task. So we will try to see through some of the experiment that whether it is possible to get the generalization concept in the few shot learning along with some work which is being done in the few shot learning. So we all are aware of that what we do in case of machine learning and the deep learning. Basically, the machine learning, it's the type of your intelligence, artificial intelligence, which uses the data and algorithms to trying to mimic the way the human people learns and does some job. We all know that the human mind learns those particular things, and over the time it gets corrected also, means it is getting the more information while doing the job also. The same thing we try in our artificial intelligence in terms of the machine learning. So what we do, we basically trying to fetch the information from the data itself, rather than concentrating on the predetermined equations. We have observed that machine learning algorithms may not be suitable or sufficient or good enough to solve some of the complex problems in case of image segmentation or NLP or the speech recognition and so and so. So we thought of having some new version. So instead of getting the traditional machine learning algorithms, we have gone through the deep learning approach, where the number of layers could be depending on the requirement of application 3, 4, 5, 6, and so on. Now this that theoretically, what we have observed, that the need of the hidden layers depending on the kind of features that we want to extract from the input object. Because to recognize or to classify or to do the segmentation, the very first and last requirement is what? To understand the features completely, so that we can do our job properly with the better accuracy. So in the both case, if you look at the machine learning and the different deep learning algorithms, we have observed that we required a lot of data, very large amount of data with the computational power. Now, there are some cases where these algorithms may struggle with real-time data. For try example to make you understand, let's say you have developed some learning algorithm to recognize the school buses with the yellow color. And the performance of your model is very good, maybe 99%. But the moment I am giving the bus, but the color is now blue. This color you can assume as one of the attributes or the features of the input. So your model may not be able to detect the blue buses. What I'm trying to say, if you are changing the input little bit, one or two features, so your learning algorithms may not perform the way it should be. So as a conclusion, we can say that our model fails the moment we are giving the some unseen data. So in fact, if you'll observe carefully these models, the learning model, machine learning or deep learning, or in fact the CNN and all, this model looks like a black box. I will tell you the research point where people are trying very hard. Since many years we are developing this machine learning or deep learning algorithm, but it is not being used in some critical cases, real-time cases. One of them is the medical. Reason is what? Whatever the results we are getting, or whether it is success or fail, you don't have any clue that why I am getting this result. That means you cannot debate on the result. Whereas if you look at your procedural language or programming languages or the traditional languages, whatever you have learned that languages, whatever output you are getting, with the line of the instructions, you can always debate that why I am getting this result. So these models you can assume as a black box. Let's say to classify the some CT scans, you have developed the model, and if some doctor asks that why I am getting this result, your model will not be able to correctly identify the reason. So these are some problems that we are facing in the traditional learning algorithms. So one of the problem is what? One of the problem is we require the very large amount of data for performing, for getting the better performance of your model. Another is the generalization. So many of you must be knowing that from a small data set, we can create the large amount of data set by using the technique data augmentation. In data augmentation, those who are aware of the image processing, different techniques like we use the different transformation, twisting the original figure, changing the dimension, changing the intensity, so and so, we will get the different flavor of this same input. So by using the data augmentation, you can create the some more means you can get some more data. From the low amount of data size, we will get the better amount of data size for doing the experiment on a DL or ML. But now question comes is, what is the cost of doing this data augmentation? If we really trying to get the large amount of data size from the low data size, then the cost of doing the data augmentation is very, very high, as well as the time consuming process. So many times it may not be very feasible. For example, if I'm asking you, let me give you the sum of the CT scan of the brains, and you want to generate some more data set artificially, looks like a real, but artificially, by using the data augmentation process. But whether the output of data augmentation is correct or not, what you required to do some annotation. So who will do the annotation? Experts. Now the question is, can you will get the resources? Here resources is the doctor. Whether the doctors are available, experts are available to do the annotation of the output from the data augmentation. Do they have the sufficient time to do the annotation for the large amount of data size? So and so. So these are some real tough time situation where even though we have the data augmentation to increase the size of data set, this process may not be adopted in many cases. So very big data set we don't have. Data augmentation may not be feasible. So for such cases where you have the one or two different samples only for each classes, can we learn it? That is what we have to do, the certain kind of innovation. So what you require? You require to handle a situation where you don't have the big data set. You have the data augmentation techniques to increase the size, but you don't have the experts, you don't have the time, you don't have the money to do the annotation for the large data set. So ultimately you have to think of how to do the, or how to learn from a small data set. So this is what we have to think in a different way. Now, one more is, if you have some supervised deep learning model, so this fully supervised deep learning model, and if you are giving little bit new images, unseen image, this supervised deep learning model will work, provided again you are giving the training for the new data set completely. That means what? It looks like it that your model is learning again from the beginning. So again, it is the time consuming process. So the fully supervised model are basically not flexible. It will face the problem, or it will degrade the performance in terms of accuracy and the other the performance parameter. So we can solve all these issues by using the technique, or by using the new approach. We call it as few short learning. So this is what we are going to understand is today's session. Okay, that means what we will be handling means we don't require the big data set. With the small data set also we can do the learning. So that we have to understand how it is being done. So the name itself, it suggests you few sort. You have a small data set, then also we are able to do the learn, the artificial intelligence. Okay, so here if you look at this figure, the training set, and there is the new term is coined here is support set. In the training set, it will look like that you have the very sufficient data size, but the images, if you look at very clearly, and the images under the support set, it's different, completely different. That means what? This support set will give some extra information to your model, so that in future, if you are getting the similar images, it can. Now here, if you want to do some comparison as a fundamental concept, let's say your model is being trained on this training data set. And now if you are giving this image, actually this image is not present anywhere in the training set. So whether your model will recognize this image correctly, will classify this image correctly? No. Reason is what? Your model is not aware of any features of these images. You have done a very good training on this, but the moment we are giving the new, your model will not be able to recognize, will not be able to classify correctly. So what you can think of, can I give a small set of this new set to make the model understand some new features? So here it is not that we are saying that your model will be learning this model completely. No. That's some features which were not present on this. Only those features I will give it to your model so that it can learn. So the name itself is saying is what? We are supporting our model by giving this image which are very small in size. So as we can understand with the previous figure, training set, which is actually a big, whereas the support set is very small. In each class, how many classes we had in the previous one? If you'll see, I can say this is the first class, this is second class, and this is the third class. And in each class, we have only 2 sample or images. So one terminology that we need to understand, the K-way and sort. K-way means in your support set, how many classes we have. In the previous figure, the 3 classes we had. So we can call it the 3-way. And in each class, how many samples we had? The 2 samples. So we can say the 2 sorts. So you have the few sort learning, 3-way, 2 sort model. So this is the technical term that it will make you to understand better. Now, try to understand with some very fundamental example, the few sort learning. Actually, this the basic idea of FSL is to what? Is to train a function to predict the similarity. Very simple. In one line, we can say what we do. We are trying to find out a function or train a functions which will predict the similarity. So, for example, I'm saying the 2 images you have or 2 sample x and x dash, and you have the one function, the similarity function. It will measure the similarity between these 2 samples or images. If this function, the same x and x dash, if it returns the 1, that means what? These both images are same. Means you can classify these 2 images into one class. And if it is 0, that means this image and this image are not same. So very simple as a theoretically concept to understand the few sort learning. So that means what we have to do, we have to think of a function which will basically try to find out the similarity between the inputs or the objects. Here, let's say you have this support sets. You have the one model, the few sort learning model, and in the support set, if you will see the 4 different classes you have: class of cat, class of monkey, lion, dog. The 4 class, and each class you have the only one sample. Okay. Now, this is the new term I am coining here is the query. Query means what? This input you are giving to predict whether this image belongs to this class, or this class, or this class. Means the dog class. So what you can do is, you have the one function left f, where you are giving the image, the query image, and the another image from the support set, let's say this. Between these 2, you will find out the similarity score. Assume that the similarity score of this query image with the cat class is 0.6. Similarly, the similarity between this query image and then the monkey class is 0.4. Similarity between this query and the lion is the 0.2. And the similarity between this query image and this dog class is 0.9. Based on this similarity, we can say this query image belongs to the dog class. Even though these 2 are the 2 different images, for the machine, if you'll see that these 2 are the 2 different images. But based on the features of the query image and the dog image, it find out the higher value for the similarity, and your model can predict that this query image is nothing but this belongs to the dog class. Now, some more fundamental. In the few sort learning, we learn for the anomalies. It will help you to reduce the data cost. We all know that for data collection and annotation, it always comes with a very high cost. So, and in FSL, you don't require the very high data set. So actually, it will help you to reduce the data cost. The FSL, it will try to learn like a human mind. We all know that for human mind, you don't require the very large amount of data set. With the one or two samples, it works like a see and the spot. The only one time it will show the some images or the object, next time your mind will able to predict it. So what we are saying, we are trying to get that concept in the machine with the help of the few sort learning. Another the part of this few sort learning is where we can apply. So the domain is image processing for character recognition, image classification, object recognition, object tracking, image segmentation, video processing. We can use for the in the robotics domain, we can use in the new drug detection and so on. So you can see the almost all the some complex applications where we can think of the few sort learning model. Now here the types, because this will help you to create your own model. The very first, the FSL, which will be the based on the metric space. One of the metric space that we have just now understand is what the similarity. So we have the some networks, the same is prototypical relational network, which comes under the FSL. Another type of the FSL that we can do with the help of the initialization, MAML and the reptile. What is the meaning here is the initialization. Whatever the model you have, machine learning, deep learning, FSL and all, the initially your neurons is being initialized with the random weights. And with the many epoch or many iterations, we are trying to optimize the way to get the better result. And how do we do the optimizations? The traditional method is what? Gradient descent algorithm that we use. So if we use those traditional process here, the cost is very high. So if we'll do the something more so that the convergence will be very fast, we have the sum of the few sort learning where the initialization time will be reduced, and we will see how it is being done by using this model MAML. Another is the optimizer. Actually, your algorithm optimizes the weight by using your traditional of the method is the gradient descent. But instead of using that, why not you are having the altogether one different network, the meta networks, which will optimize the base networks. Base network means where you are actually trying for your doing the some job. And this will help you to optimize the weights of this base network. We will try to understand with the help of the example. And the one is the last type, which we are not interested, based on the data. I think you are aware of the one of the network, the GAN network, generative adversarial network, which helps you to create the many more images from the one image. That means you can increase the data set, size of the data set. You can use the different image processing technique, the translation, flipping, sharing, scaling, reflection, cropping, rotation. These all will help you to increase the size of the data set. Now, the very first FSL that we are trying to understand with the help of the metric space is look at here. Let's say you have the two network model A and B. Initializes with the same bits. Now, two different images in X1 and X2 we are giving to this network A and the network B. And whatever embeddings output of these networks we are giving to this energy function. Here energy function could be maybe the cosine similarity. which will find out the similarity between the embeddings of this network, embeddings of the network B. It will find out whether it is similar or dissimilar, and if it is similar, what is the score, so and so. So this typical network architecture, we call it as the same-ish network. Means based on this architecture, you can think your own model to develop, which will help you to get the one FSL. Okay. Another is prototypical. Try to understand what is the architecture of this prototypical network. Let's say you have this support set. How many classes we have? Only 3 classes: lion, elephant, and duck. Now in each class, the only 2 samples we have. So what we are saying, we are using the one embedding function. This function, how can you implement? Might be using the some CNN model. By using this CNN model, you will try to extract the embedding of the each sample. So how many samples we have? 3 classes, each class the 2 samples, so total number of 6 classes. All these 6 images, you will get your embeddings. Okay. Now output of this, your whatever the CNN functions we have used, we are getting these embeddings of the each sample. Now try to find out the mean of the embeddings of per class. So how many classes? 3 classes. So 3 embeddings, mean embeddings will be getting. Now this we are representing on the space diagram, the C1, C2, C3. Done. Here, after doing this, let's say this is your query point. Now if you look at this query image is completely different from the images that you had in the support set. So what we are saying, we are trying to find out the similarity. Word same and similarity is the big difference. We are using the same CNN function which we have used here, embedding function. Now this embedding functions will give again what? The embeddings of your query image. Now this query image, we will try to find out the Euclidean distance. We are calculating the distance from this C1. The query image is placed here, and now we are trying to find out the distance from C1, C2, C3 by using the softmax, which gives the result 0.9, 0.0, 0.1. That means what? This query image is more similar to this. So you can classify this as a line class. This is what we do in the architecture of the prototypical network. The relational network, understand here. In the relational network, we are using the 2 different functions. One function in the embedding function here, another function that we use the relational function. And how do we implement these embedding functions? We can implement by using some CNN or relational function. One of the architecture is being shown by using the DNN, deep neural network. We can implement this relational function. Now, what is the use of these 2 functions? It's a very simple. The same embedding functions, you give all the sample sets. It will create the embeddings for each classes. How? For each samples you are getting, for each class, you can create the mean of that embedded matrix. Now, once you are getting the feature vector or embeddings of each class, the same functions you use for the query image also. Now, output of this function for query image, you will get the feature vectors of the query image. Now, you do the concatenation with the query image and your sample classes. And now, here you will be using whatever the output of the concatenation you will be giving to this relational function. And these relational functions will give you some value. That means how much it is related with your support set classes. And based on the value of the relational score, we can classify your input, the particular class. So here input is 0.8. So this I can say this query image is very similar to this class, the dog class. Now learning the initialization, it is again very good concept. One of the model, we call it as the model agnostic meta learning, in short MAML. Okay. Now what we do, let's say you have the three different tasks, T1, T2, T3. So initially what we do for all these three tasks, we are initializing the neurons, the random value, let's say the theta. Now, whatever the network that you have, means your model, you are trying to minimize the loss of the initialized weight by using, let's say, the gradient descent, and with the many epochs for the doing the work task T1, we got the optimal value of the weight, let's say theta 1 dash. Similarly, the second model with the second task, we started with the theta and we got the optimal value of the weights where the loss is minimal. By using the same gradient descent approach, we got the theta 2 dash. For the task 3, we got the theta 3 dash. Now here, if you'll observe very carefully, if I am getting the another task, the similar task T4, and if you are initializing the model for doing this job, again from this starting random value, so we have to travel from here to here to get the optimal value. Until unless we get the optimal value of your neuron weights, the performance of your model will not be good. So can we think of something more here so that the convergence of this optimal value will be very fast? So what we can do, look at here. Instead of, you can think of the one point, something like here, which is nearer to this similar task, the T1, T2, T3. That means what we are saying, dramatically, if you'll understand, instead of traveling from here to here, and from here to here and here to here, why not we are starting from this point? Starting from this point means this time that we have consumed, we are cutting. So the convergence from here to this optimal value will be very fast. And that is what we are doing with the one of the different types of the model in the FSL. We call it as learning the initializations. Okay. Now learning the optimizer. Try to understand with the help of this. Instead of using the gradient descent in your model itself to optimize the weights, what you can do, this is your, let's say, the base model. And here you are using, let's say, the RNN, the recurrent neural network. Whatever we have done, then the weight will be transferred to this RNN. RNN will be doing the optimization. It will again give it to this. It will check whether it is working perfect or not, and based on so on. Then you will say, then what is the importance and the unique thing about this? Once this RNN is optimized, this same RNN can be with the many different models, not only with this base model. So now these other base models will be getting benefit from this RNN model. So the computational time will be very less for the other models. Okay. Now some of the work we will try to understand, then it will make you understand in much more better way. Let's say one paper which is being published in IEEE Transaction and Medical Image, the self-supervised learning for few short medical image segmentation. The three different kinds of the data set is being used here: the abdominal CT scan, abdominal T2 SPI, MRI, and the cardiac MRI. Look at this here. Try to understand this model, which is very interesting, the very good word. Here you see the only one unleveled image you have as an input. Okay, the CT scan. I'm calling it unleveled image. Now with this, the whole operation is being divided into two parts. One is offline work, another is online work. Now what we are doing here is, from this image, your input unleveled image, you create the super pixels, the graph of the super pixels. Now how do we create the pixels? First, to understand the meaning of the superpixels. Superpixels means the pixels, the collections of the pixels will have the same property or the same features, maybe the same intensity. So those pixels will be grouped together and we will represent as the one pixels. We call it as the superpixels. So in this graph, the two different type of the superpixels you are seeing. That means on this image, you look at this portion, intensity of this portion is the one, intensity of this portion could be the one, intensity of this portion is the one, intensity of this portion is the another one. So with those, what we are doing, we are creating the superpixels and the graph between the superpixels. And with this, you create the pseudo level of the candidate. So look at carefully, try to understand this image carefully. The same image here, now with the different intensity, I can say with the different color. This portion, it looks like a one image. This portion looks like a, in terms of the intensity, this portion is something different. This portion is something different. This portion is something different. That means what? I can say you have the different patches in this image. Now what you can do, from this, you select the sum of the patches randomly. I'm saying the randomly. Randomly we have selected. So let's say I'm selecting this portion, the part of the your patches. And here, this is what your original unlabeled image. This image is what? Original unlabeled image. And this is what? From here, the randomly some patch you have taken out. So we are representing mathematically, let's say with this. Now what we are saying, on this and on this, you apply the intensity and the geometric transformation to get this image and this image. Mathematically, if you look at what we are saying, this function is what? Geometric transformation. Sorry, the intensity transformation. So this image, if you look at this original image, intensity of this image has changed. I have applied this some function of the getting the intensified. And now the next geometric transformation. Geometric transformation means what? Here in this figure, manually, if you look at the orientation of this image and this image has changed. Little bit angle has changed. So I am applying the intensity transformation function Ti and the geometric transformation Tz on the xi. Xi is what? This is your original image. Okay. Now, after doing this, what we are saying, the upper portion looks like your support set, and the lower set is what is prepared for the query set. Now here you have the one network, ALP network, Adaptive Local Prototype Pooling Network. This is the meaning of this network. We will see in detail in the next slide. But before going into detail of this slide, you output of this is what? You have the some transformed pseudo level. On this, the Sovel filter is being applied. The Sovel filter is to basically to get the boundary of that image. I'm getting the boundary of that image. We find out the loss. If the loss is very high, give the information to this network. You do the many iteration to minimize the loss, and finally it will be able to classify the patches. So now, important point to Bezier is what? How many images we have used here? Only one. Okay. So this is the one-way segmentation in the few sort learning. Now next, quickly we will understand the adaptive local prototype pooling network. Look at here. This is your support image. This is your query image. From the support image, you have used some embedding function. The same embedding function for the support image and the query image. Try to correlate with your type of the FSM. From that, we are extracting so we are getting here support feature map and the query feature map. And by using the support level, which we have extracted in the previous, with this network, you are getting the two different output. One is the foreground protocol, another is the background protocol. From where? From the support features. From the support features, we got this. Now what we are saying, from the query feature maps, we will try to find out the cosine similarity with the foreground and the cosine similarity with the background. So that's why here it is the cosine similarity function is being used. And this is the output of the cosine similarity. With the foreground and the background means how much your query map is similar to the foreground and the background of the support image. And that is what is the one-line statement of the FSL. We will try to develop a functions which will be used as a similarity function. This is what we are doing here. Okay. Now, after this, we are trying to find, you are using the softmax function to find out the class-wise similarity. If you have the, let's say, the many classes, so class-wise similarity will find out. And finally, we will predict whether the input belongs to the which class. Okay. This is what is being done in this work. Another work is what interactive few sort learning. It's again important one. You can understand easily. Here, the autoencoder function is being used, the network, the encoder and decoder. This is what bottleneck. This is the traditional architecture. Whenever you will use the encoder, decoder, in between you have to have this bottleneck network so that the exact information should not be passed between the decoder. The fundamental concept is what? This encoder will compress your original image and it will try to get back the original image after the decoder so that they will learn in a better way. Now here what is thing, why it is being called the interactive, whatever the output of this network, encoder decoder network, manually, that's why the word is being used in the interactive. Manually, one experts will indicate what is the error in that output of this encoder decoder network. Okay, that means experts will give the some input to correct the whatever the output is being given by the encoder decoder, and this process will repeat and we will get the very minimal loss, and your network will be ready to classify or doing the segmentation. Okay, so here you see this is the your masking, whatever the input side you have in the different channels. From that we are extracting the foreground and the background. Finally we are creating the vector. We are performing the concatenation from your vector, and let's say this is your query images. From the query images you have created your vector, and then finding out the cosine similarity to find out whether this query image is similar to this support image or not. Now you to look at this, the model, the very first sample you have given, and the output of model is being here now. Now, your experts, maybe your doctor, will indicate that this point, look at this here, the one very small dot has been shown. These points need a correction. So again, with this information, we are giving to the model to optimize further. From here, again, I am getting, in this way, it will be doing the iteration, maybe the 10 times, 15 times to finally get the very minimal loss. And then your model will be ready to do the segmentation. Now, here with this work, I would like to make you understand why do we need the many cases. This whole world has gone through the one trauma, is the novel coronavirus. In 2019, it started, and we all know that what has happened. But there was a very big confusion for the doctor or the experts. Reason is what? It was very difficult to distinguish whether it is corona or the pneumonia. The patches of the pneumonia in the medical image both looks like the same. Then how, that was the big difference. So people were not able to understand whether it is pneumonia or the coronavirus. till today we are not aware of, at least with the point of data, means how many people died because of the pneumonia during the corona period. But everybody is saying that died because of corona, but could be the pneumonia also. So when it started, you can visualize that we don't have any data set readily available for doing the any kind of the machine learning model. The few samples we had, nobody has collected, no hospitals, no country has the data set. Then how can we do the learning process in this? So that is what the rare cases, rare disease, we can think of the few shot learning. So here the some images which we have used, the NCIP, this novel corona infected pneumonia. This is the pneumonia or the lung cancer disease. These three are very similar, but people were not aware of. So what we can do, people might be having the pneumonia or the lung cancer disease data set. You might be having the very one shot or two samples or three sample of this coronavirus. With this sample support, by using this training data set, can we think of doing that artificial intelligence learning? Yes, is possible. So let's say you have data set of the lung cancer, nodule cancer. With this, you are basically doing the lesioning labeling. Then by using the some segmentation model, you do the lung segmentation. Then you perform the lesion locations. Then lesion segmentation. You are interested in the area of interest. And finally, by using the submodel, you can do the classification. So any model that FSL, the different types that you have gone through, you can use. But this example will make you to at least feel that why do we need the few shot learning. Now, here, because I need to wind up in next 10 minutes, to try to look at the some experimental result which will be helpful to understand whether generalization is possible in case of the few shot learning or not. We have understand with the very large data set, the generalization was a problem, because we have seen the one toy example that one model which are able to recognize the yellow school buses correctly, but blue buses, school buses not. Because this we can conclude that the new data set, the new features was not understood by the model. That's why it was not classified as a school bus. Then how it is possible to do the generalization in case of the few shot learning? So for this, what experiment is being done? Normally, the cancer diagnosed by the microscopic biopsies or histopathology. Now, if we look at the process or procedure of the histopathology, it is so complex with the very slightly carelessness, the new pathologist may detect the wrongly, means the wrong decision. Here I want to share the one data. I'm sharing the data of the USA. Then you can think of in case of India, 25% patients die just because of the wrong diagnosis. Here I cannot say that the people are not experts. Means the experts can also do the some mistakes, and the diagnostics, if there is a mistake in the diagnosis, in thing. One statement is like, if your diagnosis means the doctor says that you don't have the cancer, but actually you had gone. Another case is you don't have the cancer, and doctor's diagnosis is what? You have the cancer. So treatment will be started for the cancer for you. So what will happen to you? You can imagine. So this is very uh, serious issue in the medical domain. So here in the experimental case, what we have taken the three different data sets. One is the breast cancer histopathology, another is the lung cancer, another is the colon cancer histopathology. And we have used the both network, prototypical network and the MAML simultaneously on these different data sets. Little bit about the data set. The breast carcinoma subtyping dataset, histopathological dataset, where it has the tumors, the benign tumors, atypical tumors, and malignant tumors. These are the different size of the different category. Means you can say in this dataset, you have the three classes: benign tumors, atypical tumors, and the malignant tumors. And in that classes, these many samples you had. Okay. Another data set is the breast cancer histopathological image classification. The two different class as a measure. In that we have these many subclasses. Okay, with the different magnifying factors. This is the size of the each samples in this data set. Another data set, the breast cancer histopathological images. 1, 2, 3, 4. Normal, benign, situ carcinoma or invasive carcinoma. These are the classes we have, and these many are samples. Similarly, the another data set, LC to 25,000. This is lung and colon cancer histopathological. 1, 2, 3, 4, 5 classes we have, and in each classes these many samples you have. These are the images of your sample. Now, try to understand here the result. The very first result is for the two-way, two sort, two query. Two-way means the two class you had. In each class, the two samples you have, and here the two queries you have. Okay. Another results, other results. Just a minute. Hello. हेलो, क्या लेके आए हैं? कौन बोला है? हम लोग बुक नहीं किए हैं. आप 301 में गए हैं, तो हमको फोन कर रहे हैं 505 को. Okay, sorry. So here the another result, the three classes, each class the three samples and the three query. Another experiment was done on the 5 class, each class the 5 sorts and the 5 query modes. Now try to look at the results. Here the accuracy in case of the two-way, two sort, two query, training accuracy is near about 0.9, validation accuracy is near about 0.8, and testing accuracy is 0.75. Okay. But now the way we have increased the number of classes in the three-way, and each classes we have increased this. Here the training accuracy is less than 0.8, which were here we were getting the near to 0.9. Now it is somewhere 0.75. Testing accuracy here in this case is what? 0.6. Here it was nearly 0.75. In the same way, in the five sort, if you look at the testing accuracy has dropped something like the zero point 0.4 through or 0.43. The training accuracy has also dropped down, and here the validation accuracy is also gone down. Now, what is the reason? The conclusion is the moment we are increasing the number of classes, here 2 class, here 3 class, here 5 classes. The moment we are increasing the number of classes, the complexity for the model is increasing. So your model may not be able to recognize for those, or the performance of the model if may degrade if you are increasing the number of the classes. It may work very perfectly if the number of the classes is less. This experiment was done just because to understand if you are increasing the complexity. Complexity means what? For one model, it has to understand the 10 different classes. Or the one model, it has to understand, let's say, in case of the medical, if the only 2 classes are there, suffering from the cancer or not. It's good. With a few short learning, it will work. But if you are increasing a domain where the number of classes is increasing like 5, 10, and so on, that means in those multi-classifications, the models you have to check again whether it will work perfectly or not, right? So this is what the conclusion of the prototypical network. Similarly, in case of MAML, we are getting the same thing. The moment we are increasing the number of the classes, here you look at the 5-way, 3-way, and the 2-way, the accuracy is getting degrading. So now we have to think of what? The model that we are proposing under the category FSL, which one is correct? Which model we have to select? If we are increasing the number of the classes, so how we have to cope up so that the performance of your model should not degrade? These are the some key issues that we have to take care while developing the few short learning algorithm. But it is clear that with a few sample also we can make our model to learn the way human mind works. We can create a learning algorithm with a small data set, or maybe the rare disease data set, and so on. So with this, I will stop my lecture. If you have any questions, please.
If any questions, please you may ask. From sir. Any questions, please you may ask from sir. No questions? Okay.
So, thank you, Dilip.
Yes, yes, sir. So thank you so much, sir, for providing us with your precious time and knowledge. Your lecture on classification of medical image was very informative. You informed us how ML lacks solving of complex problems, how deep learning algorithms struggle with real-life data. You also told about the various issues faced by traditional ML algorithms, from requirement of large data set to data augmentation not being feasible. You did on few short learning was very comprehensive. You told us about the importance of FSL. Thank you once again, sir, for your contribution toward this STC. Thank you, sir.
Okay, bye.
So just wait for a few minutes. Our next resource person will be online. Our resource person has joined. A very hearty welcome to our speaker, Dr. Mohit Kumar. We are delighted to have your presence in our STC for providing your valuable time for this STC. I'm going to introduce about him. Dr. Mohit Kumar is an assistant professor in the Department of Information Technology at Dr. B.R. Ambedkar National Institute of Technology, Jalandhar, India. He received his PhD degree from Indian Institute of Technology, Roorkee, in the field of cloud computing 2018, an MTech degree in Computer Science and Engineering from ABV, Indian Institute of Information Technology, Gwalior, India, in 2013. He has received his BTech degree in Computer Science and Engineering from MJP, Rohilkhand University, Bareilly, 2009. His research topic cover the areas of cloud computing, fog-edge computing, Internet of Things, predictive learning, blockchain, and artificial intelligence. He has published more than 40 research articles in reputed journals, IEEE transaction, and international conferences. He has been session chair and keynote speaker of many international conferences, webinars, FDP, STC, India. He has guided 6 MTech theses and guiding 5 PhD research scholars. He is an active reviewer of several updated journals and international conferences. He is a member of the IEEE. Welcome, sir. Over to you, sir. Please.
Thank you, sir, for the nice introduction. And okay, so I'm sharing my screen, please. Yes, I
Yes,
am screen visible.
yeah. Slide is visible, sir. Voice is also audible. Yes, continue.
Okay, so good afternoon to all, and thanks to Dr. Dilip Kumar Chobe for inviting me for the expert talk in this FDP. So today I will discuss the one of the topic AI empowered edge resource management for IoT applications. If you look at the topic, we have the five keywords: artificial intelligence, edge computing paradigms, management of the resources, and last one is the IoT applications. AI means that we are applying some intelligent technique to get the some result from the data that is basically we are receiving from the IoT application or IoT devices. The edge paradigm is basically edge computing. Basically, we are performing some computation or storage over the edge devices for the latency sensitive IoT applications. Otherwise, we can move to the cloud computing. So, I will discuss terms. There is a table of content that I will discuss. First one is the briefly discussion about the IoT and why we need the cloud computing for the IoT applications and what are the limitations of the cloud computing. Then why we need the fog or edge computing. How AI is helpful to the management of the resources. Resource management means that the computing resources of the edge or cloud. Now, one of the case study that is basically based upon the smart healthcare system, that is basically theme of the this FDP. So now I will start from the basic of the Internet of Things. So when we talk about the Internet of Things, that is basically proposed by one of the researcher that was in the name the Kevin Ashton in 1999, and he is known as the father of the IoT. So basically, IoT is basically a device that have the capability to connect with the internet and that have the capability to collect the data from the physical environment. That is basically IoT. So when we talk about the IoT devices, that basically consists of the hardware with a sensor that can transmit the data from one device to other device or one place to the other place over the internet. So the IoT device is basically consist of the WSN, softwares, actuators, actuators, and computing devices. As you know that it consists of the sensor. Sensor is basically just like the input device. You collect the data with the help of the sensor, and there are different type of the sensor based upon the applications. If we talk about the healthcare application, there will be different type of sensor that collect the data based upon the healthcare. Okay, BP, we collect the BP, heartbeat rate, or other type of data. And when we talk about agriculture, there will be a different type of sensor. We can collect the temperature, pressure, and several other type of the information. And the other field, just like the smart home, smart city, there will be a different type of the sensors. Okay, so this is basically the input device that will collect the information from the physical environment and provide the input to the system. So these are the sensors, and here will be the system or computing device that provide the output, and or we can say that here will be the microcontroller or other type of things that will compute this information, and we find the output, and that output basically actuators forms. So this is basically providing the response to the end user. So IoT basically the network of things or physical object that embedded with the software, electronics, sensor, network connectivity that are enable these things and communicate or exchange the information between the devices over the internet. When we talk about the IoT, so each object in the network has a RFID, radio frequency identification ID. All of you heard about this term, so I briefly discuss. So these terms have the two important components. One is the tag and other one is the reader. Tag is basically what the data we want to read. So that data is basically in the encoded form and kept in the tag. And that tag consists of the integrated circuit and the antenna. And that is basically used to transmit the data to the RFID reader. So there are two types of the reader, passive reader and the active reader. The main objective of this reader is to read that particular data from the RFID tag. The network of device able to configure themselves automatically and connect the smart object with each other and with the internet for exchanging the information or data. So the IoT basically we are using to make the environment smart, due to which the human life become the more comfort. We are using the use of the AI, use of the IoT to make the human life more comfort. That is the basic objective of the IoT. If you look at the how to flow the data in IoT data. So suppose here we have the sensor and the devices, and through those devices we are collecting the data. So after collecting the data, there will be some IoT gateway or Wi-Fi or any other access point through which we start to communicate. We are basically sending or transferring that data. So this is basically connectivity devices. So through which, suppose we are sending the data at the nearest location or network edge or edge devices for the analysis or perform some computation in the limited amount of time, or we can say that in the quick session. So we are start to perform the analysis over the data that basically collected by the IoT devices or sensors. Now, after perform the analysis, we store the data for a limited amount of time over the edge devices. And after that, if you look at this one, this portion, here the data is basically in the form of the motion. Data is in the form of the motion. Data is moving where we at that place where we collect the data and up to the network edge where basically we are performing the operation over the data. After that, we can send the data to the cloud for the further reference or further use or some information. We can perform the operation over the data over there, aggregation, what types of data we require from that. We can analytics, we perform the we basically analyze the data, and lastly we save that particular data for the further reference, because we cannot save the data at the network edge because it has the limited computation as well as the storage capability, and we don't have the so much capability to store the data for the long period of time. But cloud has the infinite resources, we can send the data. So if you look at these two things, the data is basically more vulnerable when data in the rest mode. And here, when the data is in the motion, there is less probability to to hack the data or to corrupt the data, or unauthorized user can access that particular data. So this is the diagram that basically I have taken from one of the article. So there are a large number of the application of the IoT. If you look at the role of the IoT and basically the AI in the field of the agriculture, in the field of the education, in the field of the smart city, smart home, ATC, and healthcare system, the many more areas. Most of the areas, smart building, energy efficient building. So most of the areas that are related to the basically the not only the computer science but even the electronics, and people are basically using the civil field also. So most of the areas are basically we are applying the IoT based services, and basically we are applying the AI based technique to find some of the relevant information or the data that are we have available. We apply the AI based technique to find the information that basically further we can use. Okay. Just one second. Just one second. I'm getting the call. Sorry for that. No. Okay. So when we talk about the IoT applications that has been adopted quickly in the large number of the areas to create the smart environment that may be the transportation system, smart city, smart home, agriculture, healthcare, and the many more. So everyone basically want to connect with the internet. Even you know that the IoT device has crossed the number of IoT devices that has crossed the value that basically so number of IoT device is uh, more than the total population of the world. Okay. Yeah, am I audible? Yes, yes, okay. Yes, yes, sorry, sorry. Okay. So number of IoT devices cross the total number of population. It means the huge number of the IoT devices are available. So can you assume the expected annual growth of connected IoT devices and the impact of these devices at the global market from 2012 to the 2020-25? So by 2025, it is expected that the IoT device will capture the market worth 3.9 to the 11.1 trillion dollar. Look at the diagram. These are the connected IoT device up to the 2023, and that is nearby 75 billions. That is nearby 75 billions. And this is the global impact at the IoT device in the form of billions. That is more than 300 USD. 300 billions USD. So now you can see the importance of the IoT. So the IoT has become the important and dominated part of many applications. IoT devices are basically producing the data, the heterogeneous data, that to be analyzed and required basically a platform that should have the computation capability as well as the storage capability with high network bandwidth. So that platform is basically the cloud computing. That platform is basically cloud computing. So when we talk about the cloud computing, so when we talk about the cloud computing, cloud is basically a platform or paradigms that consist of the heterogeneous resources and have the infinite number of resources basically. So cloud data center are geographically centralized, which make it non-effective to deal with the processing and storage demand of highly distributed IoT devices. What the demand of the IoT devices? It can fulfill, accomplish the demand of the IoT devices. It means it can provide the computation as well as the storage capability to the IoT devices. So it offers the large number of the resources. So it is basically the business model in which user get the on demand services over the internet and based upon the pay per use basis. It has a several characteristics, just like the demand can be changed. It means it can be increased or shrink at the runtime. So based upon that, it has the flexibility as well as the elasticity type of the services it offer. Multi-tenant environment. A single person or multiple IoT device can request for the same type of the resources, or it might be possible that several IoT devices can request for the same type of resources, or single IoT device can request for the multiple type of the resources. So it offers the multi-tenant environment. The meaning is that there is only single physical infrastructure. There is the single physical infrastructure, and over this there are multiple virtual machine resources are deployed over this one, and multiple user or IoT devices are that are basically using these resources. But physical infrastructure is single. You can take the example of the any of the building or a building that consists of the multiple apartment. Okay, they are sharing the boundary values, but they have the its own apartment. The meaning is that they are sharing the common physical infrastructure, but retaining their privacy. Okay, resource pooling, it has a huge number of the resources that can be pooled or that can be provisioned to the end user as per their demand. So broad network access, the connectivity of the network, uh, is also the important factor, and that is basically directly affect the performance of the system. The scalability due to which most of the company, academic and government organization are using the service of the cloud. It become important to integrate the cloud with the IoT. And this integration is called the COT. That is basically the cloud of things. So that is the reason to integrate the IoT with the cloud. So look at this diagram I have taken from one of the paper. So these are the basically the service of the cloud. It may be the hospital, the smart grid, uh, the responsive store, the home and energy management, traffic flow optimization. So there are the large number of service that is basically that large number of application on which that the cloud is offering the services for such type of the applications. So now a cloud offering the services to the IoT application, but what are limitation of the cloud? Why basically we need the edge computing or fog computing paradigm? So when we talk about the cloud computing, that provide many individual as well as the organization a highly available and efficient computer network. But the lag in the service that is based upon the latency, probability, location sensitive application like IoT and the connected vehicles. The meaning is that the main issue with the cloud is that it cannot offer the services that are based upon the latency. That are based upon the latency. The simple meaning is that suppose that some of the applications, just like the AR VR based augmented reality, virtual reality, now you are playing the online game. So when you are playing the online game and you enter something and that need the response in the even the millisecond, it means we cannot afford the delay even in the millisecond. So when we send the request to the cloud and return the response, we can there will be the delay approximately maybe the 50 millisecond or 100 millisecond, but we cannot afford. So the meaning is that we need a paradigms, we need a service of the cloud at the network edge so that we can reduce the delay. Other type of the application are also exist. Other type of the application are also exist where just like the connected vehicle, vehicular network, there are so many number of smart city, smart home, healthcare. So there are many applications where we cannot afford the delay. That's the reason we move to the fog computing or edge computing. We move to the fog or edge computing. So these applications which depend upon the speed of internet and functioning time of the computing service are not suitable to run the over the cloud system and cannot provide the guarantee the fast service due to large data processing and transfer. So the latency, the main issue with the cloud, and for the cloud services we require the internet connection always. Not the even the internet connection, but we require the high bandwidth. One more issue with the cloud, that is data security. The confidentiality of the data as well as uh, the security of the data. The user data is basically stored at the remote location and there is no control of the user at that particular data. So that's also issue. Several and industry had adopted the service of cloud, but due to the security reason, few industry still not adopted the service of the cloud. So the meaning is that a business model or businessman or the banking type of transaction or other type of the sensitive information a person cannot store over the cloud. there may be several types of the attack are possible over the cloud. So look, if you look at the issue and the application of the cloud of things, so smart home and smart metering, video surveillance is one of the application that require the services and cannot afford the delay in the video surveillance. Also, the healthcare, smart city, smart energy, automotive and smart mobility, logistic, and the many more. And these are the challenges. Security is the main challenge, reliability, heterogeneity, performance, large scale, and the latency. So the infrastructure of the COT cloud of things is heterogeneous in the nature, complex and geographically distributed, where the traditional cloud computing paradigms failed to process due to the high latency and scalability. This is the main issue. So many of the IoT applications that require the high velocity of the real-time analysis, online gaming, augmented reality, virtual reality, big data analysis, video surveillance, and the many more. So those applications, or in this application, we cannot process over the cloud. So we try to process over the other paradigms who can offer the service in the minimum time or without delay. So the name of the paradigms is called as the fog computing or edge computing, that is basically offer the service of the cloud at the network edge and the real-time applications for the real-time applications. So it is used to process the real-time application that are closer to data source and improve the latency, energy, scalability, and this is the network connection. Now, so the reason behind to use the edge computing or fog computing for the RT application that I discussed. So this is basically the decentralized computing architecture where data is processed and stored between the origin and the cloud infrastructure. The meaning is that this is a three-layer architecture. If you look at this one, so here will be the IoT devices, and here will be the fog or edge, and here will be the cloud. Now we are sending the data, we are collecting the data from IoT device here, and data is basically processed over the fog. If it is latency sensitive, otherwise we can offload the data to the cloud. So here the AI-based technique will work. Firstly, how we can analyze that, where the data will offload, and how to manage the resources of the cloud as well as the fog. So it provides a platform to expand the cloud computing to the edge of the network. The fog computing or edge computing that put the resources and process at the network edge and the edge of the network. Mostly on network devices. However, data will be stored only the cloud. The simple meaning that because these devices either fog or edge have the limited capability of the storage as well as the computation. So we cannot store the data for the long period of time. But these paradigms, these are the basically called the emerging computing paradigms. So these emerging computing paradigms provide the faster response time and lesser or less resource consumption. And these devices are basically for the real-time applications. So if you look at the no edge node are implemented near to end user IoT device. that mitigate the impact of the latency, location awareness, geographic distribution of unsupported feature of the many IoT applications. The simple meaning is that we are collecting the data from the IoT devices, and that place we are providing a computation paradigms, or we are providing the resources over that we can compute, or we can perform the operation, or we can basically process the IoT data or sensor based data that we have collected. That is basically the edge computing or fog computing. There is a little bit difference between edge computing and fog computing. The difference is that suppose I'm collecting the data with the sensors, IoT devices. Here I am collecting the data from these are the IoT devices, and at this place directly this device is directly this is the device that connected with the this sensor, or this sensor directly sending the data to this device, and that device become the edge device that is basically processing the data that is collected by from these type of the sensors. Now we are sending the data through the LAN cable at some distance, okay, that is near distance, and where we have a computing paradigm that may be your laptop, that may be your desktop, that may be your uh, smart gateway, that may be your smart router. So such type of the things are available. So that become the fog computing. That may be your workstation. Okay, so that is basically fog computing. So your basically your mobile device can work as the IoT device or can work as the edge device, depend upon the computation capability of that particular IoT device, that particular device. So, for example, edge computing decrease the data offload into the cloud, which decrease the response time. Undoubtedly, when you offload the data at the edge location or the edge of the network, then we can decrease the response time because your processing will be done at the local node as compared we are sending the data to the remote location at the cloud. A smart device is an edge between body things, it means the IoT things, IoT devices, and the cloud. A gateway in a smart home is an edge between the home things. Look at the diagram. These are the basically the IoT devices, okay, that are basically uh, collecting the data. Okay, so these are basically heterogeneous data and a large amount of data. So these devices are directly connected with the access point that may be connected with the Wi-Fi, that may be connected to the 5G, that may be connected to other type of the things. So they are sending the data to the fog node. They're sending the data to the fog node. If data is basically latency sensitive, otherwise we can offload the data to the cloud. And these fog node or fog devices that are connected with the network, they're connected with the cloud through the network. And here they are connected with the fog through the access point. That may be Wi-Fi, that may be Bluetooth, other type of the connected device, connected devices. So the fog node through wired or wireless access media such as the Wi-Fi, Bluetooth, 5G, Zigbee, through which it is connected with the fog node. Fog node communicate with each other through the wired or wireless media. All the fog node or edge node are connected to the cloud by the core network, Internet Protocol core network. Network virtualization and the traffic engineering are achieved using the virtualization technologies such as the SDN and the network function virtualization. That is basically internal networking that are available in the cloud computing. Okay, that basically it means the networking between the virtual machines, VMS, the virtual machines. So now we discuss the case study about the healthcare system. Okay. So when we talk about the healthcare system, so assume that if you compare the traditional healthcare system and the current healthcare system, so you will find a huge gap between them. If you start to compare that, okay, suppose in the traditional system, traditional approach, what happens? Suppose someone feeling some issue in the body, it may be the heart pain, it may be other type of the pain, or some type of other type of the issue. Okay, so they basically start to move to the hospital side. If this is a daytime, okay, working hour, then it is easy to get the doctor, but in night it is very difficult to get the doctor or get a treatment, or you will get the treatment after some time because the hospital will call to a doctor that will come in the emergency for the emergency conditions and that start the treatment. So that was the very time taking approach, because when you move to the hospital, you find the symptoms and move to the hospital, and the hospital will start, doctor will come and the hospital will start the test of the that patient and find the result. Okay, or this type of the issue, and in this time period it will take more minimum 2 hour to 6 hour. So in this approach, some of the severe cases or some of the critical cases or critical patient may be died. It generally happen. Okay, so that was the basically issues. Now when you basically start when you compare today scenario or technology based scenario, IoT based and the AI based scenario, so what happen in this case? You have the IoT devices, you have the large number of IoT devices. Suppose you are using a smartwatch that have the capability to capture the data, to collect the data. That may be the heartbeat, that may be the BP, that may be other type of data. And after collecting the that data, and that data, you have the smart app, healthcare app in your mobile phone, and you can enter the detail of that particular data to the app. And after entering the detail, you find some values. It will basically send the data to for the computation, and you find some of the value. If that value is greater than that, suppose the value is x and that is greater than the threshold value, okay, it means it is an emergency case, and you have to move to the hospital side. Okay, so now at the same time, you can send the message to the nearest hospital, as well as the send the message to doctor also. Your location is sharing, and you know it means your application know the nearest hospital as well as doctor. So message is basically sent to the hospital as well as doctor. So when you move to the hospital, patient move to the hospital, the doctor will be ready for the treatment. So this is basically time saving approach. When patient uh, reach to the hospital, there will not be any delay. All are ready, and there no need to any test cases, because all the data is already analyzed over the app or technology. What type the issue a person or patient has. So that is basically biggest advantage. So in the previous day, in the traditional approach, people moved to the hospital. The healthcare system was the hospital centric. The healthcare system was the hospital centric. But currently, we are moving with the technology. It becomes the user centric. Okay, you check the all the detail. Okay, okay, and after that it checked that, it find out that now condition is not the severe or not the any critical condition, then the technology or app or it can suggest some of the medicine to you, and you can easily take the medicine and relax at the home. There's no need to visit the doctor as well as the hospital. So this is basically advantage of the technology. It can save the time as well as it can save the money. So now IoT enabled device have made remote monitoring in the healthcare sector possible, and that basically we are basically trying to save the patient. We're basically trying to save the patient. We try to monitor the condition of the patient regularly, so that before reaching to the critical conditions or undesired conditions to the patient, we can provide the proper treatment or medicine to that particular patient. It has also increased the patient engagement and satisfaction as interaction with the doctor have become easier and more efficient. Automatically get the message to the doctor. Automatically you can get the time for the doctor time slot. This is time slot, and you can reach that particular time slot. There's no need to wait to, and you can just wait only 10 to 15 minutes. There's no need to wait the time in the queue. So IoT had the major impact on reducing the healthcare cost and improving the treatment outcome. Less time, less cost. So we require the electronic healthcare records. If you look at the smart healthcare IoT system, so IoT has the four-step architecture that are basically will explain the four-step architecture. Okay, the first step is basically we collect the data. How to collect the data? To collect the data, we tell to the sensors, and after collecting the data, there is input form, and after processing, the actuators basically provide the response. The actuators are available: monitor, detector, camera system, and these are the devices are required to perform the operation over the data. It means to collect the data, find the response of the data, what type of data is available. Now, after collecting the data is basically in the form of the envelope. Now we need some function, the aggregation function, another type of the function or operation to convert that analog data in the form of the digital data. Once data is converted in the form of the digital, digitalized, then we perform the AI-based approach, ML or DL-based approach over that particular data. It means we can predict the what type of issue or disease available in the patient, or what a possibility of this one. So now we can send the data to the cloud, and finally advanced analytical approach we can apply over that particular data, and that basically will be helpful for the further reference. And if we find something, some special cases, we can share that data to the other doctor also, and that would be helpful for the other one. So this is basically the four-step healthcare system. Now, autonomic edge cloud assisted framework for the heart disease detection using the random forest logistics regression. So this is the title of the work paper that had been published in the multimedia tool and application in this month, in the last month, so in the month of the April, and this is the one of the SCI journal. Okay, Q1. So now what basically we did in this paper. Okay, so if you talk about the basic of the this one, so as we know that how basically number of the disease are increasing, that the reason is that we have decreased the physical exercise. We have decreased, basically we are basically busy in the office life, or we are basically busy in the mobile phone, we are busy in the, to watch the TV. Basically we have reduced the physical exercise, And when we reduce the physical exercise, the meaning is that number of disease has increased in our body. Okay, that lead to several health related problems or issues. So it is not easy to detect the health, a heart related disease or any disease, but due to the advancement in the technology, the fog computing, edge computing, ML, cloud computing, IoT, we can basically we have the large number of the framework or the applications that can detect the disease based upon the data. So every IoT device that want to connect with the internet and offer the ubiquitous service and produce a huge amount of data. Okay, so IoT device, the limitation of the IoT device is that it has the restricted or very limited amount of the battery as well as the computation capability. Okay, so the healthcare data, how to basically check, how to basically predict that particular disease of a patient. So we required a platform. So the platform may be the cloud platform, that may be the edge platform or fog platform. So we cannot use the cloud platform if there the patient in the critical condition and where basically we cannot afford the delays. The latency based applications. So where we basically apply the edge paradigms. We apply the edge or fog paradigms that has been introduced to overcome the bottleneck or issue of the cloud platform and that bring the resources at the network edge or close to that location where we have collected the data from the sensors. It improves the various institutional parameters or various previous parameters like the energy, response time, scalability, as well as the delay. So the edge computing and IoT of the paradigm improve the innovative solution to the healthcare application where delay cannot be afforded for the critical conditions of the patients. So now it has been observed that some of the article, the cardiovascular disease that basically approximately 18 million lives are affected every year globally. 18 million people. So consists of the many different type of the disease. So can you assume that? Can you imagine that the 18 million people are that is basically affected from this disease, and the reason is that it is very difficult to predict the heart attack cases. You generally heard in the neighbor or in the near places or read in the newspaper, okay, these people died due to the heart attack. Generally, we always listen. The reason is that it's very difficult to find a prediction of this disease. So based upon the symptoms, based upon data, we try to predict. So most of the deaths are just because of the heart attack and strokes that are unable to diagnosis at the early stage. The reason is that the people of the world are died due to heart attack before the age of the 70 years. So detection of the heart related problems is very difficult because at many times symptoms are not likely surfacing and because of this little problem cannot be identified clearly. So what are the symptoms for this one? Many times I have seen that a patient that never come the heart attack, but the first time heart attack within the 2 to 3 minutes it will die. Within the 1 to 2 minutes or 2 to 3 minutes. The first time heart attack. So how to basically find the symptoms, how to basically try to predict such type of disease. So when we transferring the data from device to other for the storage and processing service that introduce the latency and the accuracy in the framework. So we basically have the several type of the algorithms or framework, several type of the ML based algorithm or AI based ML based models or AI based approach we have. But the reason is that the most of the approaches do not provide the better accuracy. It means the prediction approach is less. Cannot predict the properly based upon the symptoms as well as the data. That's the main issue. So to overcome such type of the techniques, we have proposed one techniques that is firstly the random forest. We have applied the random forest, but after that we basically apply the random forest with the logistic regression. We symbol algorithm. So now, so so AI basically play a significant role to predict and extract the expression information from the sensor-based collected data and provide the result. So we have used this technique, random forest-based logistic regression, and that basically what the basically we have got the output that basically improve the accuracy and as well as we basically process the data over the edge node. So we have reduced the latency as compared with the other existing algorithms. So look at the diagram. There is a general proposed architecture for the healthcare system. If you look at this one, if we talk about the smart healthcare system, so there are several components in this system. So we'll discuss the component with the one by one. First one is the IoT devices. There are a large number of the IoT devices that are basically used to collect the data of the patient, and after collecting the data, where data we can offload, cloud or phone node. That is basically also a challenging issue to find out that data. So how to basically take that decision, how to basically take the offloading decision, how to take the offloading decision, where to offload the data. Now after that, what type of database we use and what the meaning of the connectivity and how to predict that particular data and what are the storage database where we can fastly access the data, and that database may be the relational database or non-relational database. Okay, so when we talk about the patient, so there are different type of the healthcare related data are collected from the patient, and the entire data is analyzed by the various technique to find the probability that whether the patient is critically sick or not, the condition of the patient basically. Now do we have the IoT devices to collect the data. Now the connectivity, suppose we are basically providing framework, so how to connect with that particular framework. Suppose we have the smart watch, okay, so that is basically collecting the data, and after collecting the data we have entered that data to that particular application that we have, the smart healthcare application, just like the all of you have used the Arabia Setu app. Okay, so this is basically data collected in the app. After the collecting the IoT devices or manually, we can provide the information of the data into the application. Database, basically we have used the Firebase server is working as a database for storing purpose, because that basically minimize the computation as well as the cost. Medical expert means that when basically we enter the data in the applications, all the data after being stored in the database will provide the medical expert so that the proper medication can be provided to the patient, and they can also use data even after several years for the some references. If same type of the issue, same type of the uh, case is available after some year, some time, so they can refer that particular case. So that's the reason the data is stored at the cloud. So this is basically the Flex app, the micro framework that is used that is basically used to Python programming, and basically we have used the Python programming, and we have used the Google Colab type of the platform to implement this work. So Google Cloud Platform is basically used to store the data for the future reference after sharing with the medical expert. Heroku is basically one server used to deploy all the analytical tool and most of the major computation of the models, calculating the probability or predictability of the disease of the patient. And what the ML model? We have a large number of the ML model are available. So basically, we have applied the ML model based upon the data, and finally, we basically apply the random forest with the logistic regression. Now look at this one. This is basically diagram of our paper. Okay, we have basically proposed this healthcare framework. So there are the number of users that basically we're collecting the data, and after collecting the data, we start with the mobile used in the fog mobile. Basically, we have used it as a fog node. So after collecting the that data, we can enter that data in the app application, Android application. So data collection for analysis of that particular uh, we basically try to analyze that particular data. So requesting server result, we send the request after collecting the data, we enter that data into the app. So after entering data into app, now we request, we basically start to push for the processing of that particular data. It means we want to find what are the issue, healthcare issue, or what are the disease that belong to particular patient. So the request goes to the nearest server. It means the edge or for computing. Okay. So when request goes to the Heroku server, so it receives the request and it applies the ML model or AI based model, and based upon the data and the same times, so it basically find the result. So there are several types of features are available, several types of attributes are available. So based upon data along with the feature and attribute, it compute, it basically predict the output, and that output we check again, that output is providing to the user, that is basically display in the screen, and we check that that particular output is within the threshold limit or not. If that output is not the threshold limit, then it sends the automatically message to the ambulance as well as the nearest hospital. Okay, so the hospital will send the ambulance, and basically they start they basically they basically when they send the message to the hospital, and the hospital is ready for the treatment, they start or they basically ready for the treatment of the patient. Now in this way, after basically analyzing the data, if you look at this one, so we store the data at the Google Cloud Platform for the future reference. If the result is within the threshold limit, then there no need to admit in the hospital. So we just our application can suggest some of the medicine based upon the that issue, and and patient can take that particular medicine and can rest for some period of time. If you look at the one of the basically the diagram or framework, how to basically this the patient here, they're collecting the data from the patient. So after collecting the data from the patient, so this is the end user with the smart device that collecting the data, and after collecting the data, we send the data to the through the IoT gateway to the edge network, and after that it find the some of the values and check that which value is within the threshold limit or not. If not, They send the message to the hospital and it will send the ambulance for the patient. Further, it can process the data. After processing the data, it can store that particular for the cloud. This is the cloud data center, this is the edge, and this is the IoT. So if there is a very limited amount of data, the data basically we can process over within the mobile phone, then there is no need to offload the data at the edge or cloud. There is no need. But generally, the size of the data is larger than we cannot process over the IoT node. So we send where we offload over the edge or cloud. So what are the offloading issue and how to offload? So based upon the deadline or sensitive case, based upon the size of the data, okay, it means what the resource required, latency, priority. There are various factors based upon we can decide the data will offload at the edge computing or fog computing. So what are the role of the ML or AI in the smart healthcare system? Basically the role is to predict the disease with the high accuracy. The role is to predict the disease with the high accuracy. So there are several algorithms, several AI-based framework are available, and all the framework have the objective to improve the accuracy so that we can easily predict the disease, so that we can provide the better treatment to the patient and we can save the life of the human. What are the issues and challenges in the healthcare system? So there are several issues and challenges in the healthcare system. First one is the security. So the healthcare data is sensitive. Unauthorized user cannot access the data of the patient. Suppose one of the unauthorized user that basically access the data of the patient, and that patient that basically sell the data to the insurance company. Ownership of the data. Data need to come from the rightful person, not the illegitimate user. Now, low computation and storage capability of the IoT devices. The IoT devices don't have the power to compute this healthcare data. So how to perform the offloading decision and how to basically allocate the resource based upon AI based technique. Based upon the AI based technique. What the resources? The resources may be your fog node, the resources may be cloud node, cloud virtual machine, the resources may be the resources are available in the hospital. It means what are doctor are available. So resource may be anything. Responsiveness. The health data need to be continuously monitored, and any rainy day situation need to be urgently identified and reported to the doctor for the quick action. If there is a critical issue, whether the unwanted condition occur, when continuously monitor the healthcare data of patient, so it should inform to the doctor quickly so that they can provide the proper treatment to the patient. Data analysis. An intelligent system need to be designed to analyze the data based upon the healthcare data. They're based upon the historical data. We apply the AI-based algorithm, ML-based algorithm at the historical data to identify the pattern of that particular disease, diagnosis the disease, and we can prescribe the treatment and we can suggest some of the medicine to the user based upon the uh, prediction result, what we have predicted by the algorithm. So on the basis of that prediction, we can basically provide or we can suggest some of the medicine to the patient. High quality sensor. This is also an important thing. We require the high quality sensor to collect all the data in an efficient manner. Otherwise, we cannot, if we are not collecting the data in an efficient manner, it is very difficult to apply the AI-based approach or technique over that particular data. The meaning is that we require the more and more pre-processing and difficult to find the high accuracy. Difficult to find high accuracy. Now, sharing of the data. It is essential or mandatory, or we can say that it is helpful to communicate the data and any essential finding or model generated to the other doctor or hospital so that they can be benefited from this one. So if you look at the security one, is the one I basically forward one thing. The people are basically applying the federated learning approach to secure the healthcare data. The meaning is that the federated learning approach basically they are now sending the data to the outside the hospital. They are basically sending only the model. They are training the model only. So they are securing the healthcare data. So that is basically approach. A different approach are applying, and the people are also using the. There's some limitation of the federated learning. The people are also applying the blockchain approach for the healthcare data. Okay. Now, okay, this is done from my side. So, any query?
Any query, please ask participant. Any query you may ask from sir. So, okay, I think I should conclude the session. No one is asking. Thank you for taking the time and knowledge to share with us. Your presentation on AI-enabled edge resource management for IoT application was quite informative. You begin with the fundamentals of IoT devices, such as wireless sensor networks. You clearly explained how data is in motion and at rest, how it more vulnerable in the later. You also demonstrate how the application of IoT is related to our daily life. It has been quickly accepted in several areas to create a smart environment such as healthcare, agriculture, and so on. To tell us in today's environment, it is essential to integrate the cloud with IoT to process and how it is provided endless resources for computing the storage to IoT application. How latency is a measure of cloud computing and edge for computing might overcome this latency issue with adequate explanation with a diagram that's quite useful. How smart healthcare is related to IoT and four-step architecture process for the healthcare system. We learned about heart disease prediction using autonomic edge cloud assisted shop. Sir, thank you once again for your contribution to this system. Thank you, Monsir.
Thank you, sir. Thank you. Can I leave, sir?
Yes, sir. Yes, sir.
Thank
Please.
you. Thank you. Thank you.
So our resource person have joined. A very hearty welcome to our speaker, Professor Kalyan Chatterjee, sir. We are delighted to have your presence in our STC. Thank you for providing your valuable time for this STC. And thank you, sir, for accepting our invitation. I'm going
Good
to introduce
afternoon,
you.
Dilip.
Yes, sir. Audible, sir. I'm
Hello.
going to. Yes, sir. Audible, sir. Your voice is audible, sir.
Hello.
Yes, sir. Yes, sir. Audible, sir.
Okay.
Yes, yes, sir. So I'm going to introduce about our resource person. Uh, yes, Professor Kalyan Chatterjee is currently working in the Department of Electrical Engineering, IT, Aisin, where he is a faculty member since 2005. He is currently holding the position of head of the department. Professor Chatterjee completed his PhD from BIT Mr. Ranchi and postgraduate from Jadavpur University. He has guided 13 PhD scholars and 5 are ongoing. He also published 86 international papers in different doctorate journals. Professor Chatterjee also holds different administrative posts in IT as in Dhanbad, like Associate Dean R&D, Chairman of JRF Admission Committee, etc. He also successfully completed 3 external funded projects. His research interests are soft computing technique, renewable energy, power system, stability, etc. Welcome, sir. Hand it over to you, sir. Sir, you are mute, sir. Slide is visible. Yes, sir.
Now this is visible.
Yes, sir. Yes, sir. Slide is PPT is visible, sir, and voice is also audible.
Hello.
Yes, sir. Audible. Voice is audible, sir.
Okay.
Yes.
Okay. Good afternoon, everybody. Today, just present the topic is detection of the fatal disease from the biomedical signal using hybrid deep learning algorithm. First, we actually go through the how we actually feature extension problem. Then we actually consider neural network. Then we starting from the deep learning models. Now, first we for the introduction of the total presentation, we actually divide it in this way. First, the what is the main problem, how we actually formulate the problem, what is the literature review of the fatal disease. Here we actually consider the arthritis detection problem. then we can consider the cardiac arrhythmias using the novel feature extraction techniques. And last, we actually go through the deep learning methods. Now, first we understood this thing, when any disease or abnormality in the human body can be detected by the uses of the variety of the physically and the visual examination, when many human interactions are involved. Now, even today, mostly the physical and visual examination is done manually to detect any fatal disease. Where there is chance of the human error, instrumental error, or the diagnostic error. Also, conducting such physical and visual examination are quite costly, which you could not afford of the many low-income peoples. It is therefore necessary to use the non-invasive techniques for automatic and computerized detection of abnormality from the human body, in which there is the lower probability of the errors than the manual procedure. So the main aim is that, so how actually can collect the data from the human body from the computer digitally, and the lower probability of the human error also, by according and the analysis the electrical signal from the human body, which depend the functioning of the human organs. For example, the ECG represent the functional of the heart, and when you can consider the MRI represent the visualize of the brain. So this is the non-invasive techniques. We actually analysis the system is very easy way. So the in this presentation, we actually automated and the computational detection of the fatal disease with ECG signal is discussed. So the when we actually consider the ECG signals, so we actually go through the what is the different type of the signals we actually got from the human body, what is the abnormality of the signals, how we actually classified the signals. So that we actually discussed today. So mainly we emphasize of the detection of the heart arrhythmias from the electrocardiogram signal problem from the use for the, we actually mainly handle of the, instead of the MRI, we actually only handle of the ECG, mean the biomedical signals. So the selection of the ECG signal are selected based on the database availability, morality, and the non-invasive technique and the previous research. So when we actually go through the literature review, means the what is the previous work is done. Two way we actually go through the what is the actually previously how the soft computing techniques or the machine learning algorithm, how we apply it into the biomedical signal, and the recent trend when you can consider deep learning algorithm, how actually overcome the error of the machine learning system through a deep learning methods. So the two literature survey we actually represent here. So when we can go through the literature, total learning literature. So there is the three features is there. First features is the how we actually take the feature extraction techniques. Second is the which type of the algorithm we use for the training purpose, and third is the which benchmark database we mainly use. So the mainly the when we actually see that the traditional machine learning approach, so either we use the independent component analysis, or we use the discrete weight left transform. So that different, they will be mainly used for the feature extraction techniques, and the algorithm for training classification purpose we use the neural network, we use the Baposan algorithm, support vector machine. So different of the algorithm we actually traditional machine learning algorithm is there. So here we actually the right hand side you can see that the last one, what is the accuracy rate, that is also present in a system. Similarly, when you can consider the deep learning method, we actually mainly we actually the conventional neural network we actually use, and similarly the database we also use the MIT database in the system. So the main objective of the system is the first we actually got the biomedical signal processing, and from the biomedical signal processing, how we actually can predict the our arrhythmias from the ECG signals. Now the total work or total presentation we actually divided the these three parts. First, the database collection, pre-processing, mean the when we actually raw data, we actually pre-processing the data, either the denoising and the smoothing the signal. Then we have the peak detection of the ECG signals. And last one is actually the feature extraction algorithm, and the last is actually the RTMS detection. So the work is actually divided. First, we collect the raw data. After this raw data, we actually pre-processing. Then we actually find out the peak detection of the ECG signal. So different type of the point we actually extend, and after that we actually classified the total signals. So we for the introductory part of the lecture, so we actually first to understood this thing, what is actually the ECG signal, how actually you can got from the biomedical signal. The electrical activity of different human organs are represented by the bioelectrical signals, or ECG is the one of the bioelectrical signal origin from the heart. The instrument which is used to observe the working of the heart is called the electrocardiogram. It is very important to know that electrocardiogram is an instrument which uses the display the electrical signal generated due to the functioning of the heart. To recognize the anomalies of abnormality in the working in the heart, these ECG signals are being printed on the cup paper and diagnosed manually by the doctors and the experts. So you can see that when we can actually find out the biomedical signals or the ECG signals, we got the this type of the natures in our system. So there is the 5 peak is there, POA, PRQ, ST. So you can understand this thing. The recording of the ECG is done by capturing and amplifying the very small variation in the potential difference from electrical impulse on the surface of the human skin due to the cardiac function. The blood plumping phenomena by the heart either into the ventilation and to the entire body by the arteria, and ventilation is expectedly known as the contraction or depolarization, and returning to the original state or resting state or relaxation state is called relaxation or repolarization. So that mainly the we actually consider the contraction and the repolarization, means the one is actually depolarization and the repolarization. During the depolarization and repolarization, we actually got the total signal. So cardiac of the heart function is the combination of the contraction and the relaxation of the depolarization and repolarization by the synchronizing manner. And contraction and the relaxation are the
Excuse me, sir.
Hello.
Sir, your slide is not moving. Make it dynamic, please. Now it's okay. Thank you.
Okay. This slide is not moving. Anyway,
Now it's okay, sir. Now it's okay.
now this is coming.
Yes, it deflect another slide. Maybe now you can proceed, please.
Okay, 1 minute. Now this is coming.
Yes, the slide is moving. Voice is also audible. Yes, sir. Okay, sir.
Okay, then the mechanical phenomena, where is the depolarization and the repolarization are the electrical phenomena. The sequence of the depolarization and the repolarization is the synchronizing way to identify the potential difference which causing the electrical impulse, which are recorded from the waveform of placing the electrode to skin of the body. So when we can actually the ECG waveform consists of the 5 different peak, PQ, RST, sometimes the U. So if we go through this the total system, you can understand this thing. You can see that from this waveform there is the 5 wave peak is 2 peak is we mainly consider. One is the P wave, R wave, and here you can see that there is the QRS complex is there. So our main aim is that when we find out the electromagnetic signal, so we actually find out these 5 wave. Actually we can find out the feature extension of these 5 wave. So you understood this thing that every waveform, when we actually consider the biomedical signal, their certain duration is there. There is the first certain duration is there. Within this duration, that is actually got the normal operation. If the increase or decrease the duration of your waveform, then the abnormality is actually occurred into in your heart. Okay, so you can see that the P, when you can consider the P wave, that is the contraction of the arteria used for analysis the arterial rate. So this is actually 60 to 80 millisecond. QRS, the depolarization or particles contain the most significant influence of the ECG signal, that is the 80 to 120 millisecond. And you can consider RR interval. So that is actually the PQ interval duration between the P waves and the 120 to 200 seconds. So understood this thing. So 5 different waveform peak or duration you can understood this thing. The P wave, QRS complex, and the T. This is the 3 wave we actually mainly got from the ECG waveform, and depending of the your health, heart health, so we actually got the different type of the segment. So that point of the view, we actually consider the amplitude and the duration of the waves, interval and the segment of the ECG signals. So the features of the P wave, the amplitude is the 0.1 to 0.2, and the duration is the 60 to 80. PR interval is the 120 to 200. PR segment is the 50 to 120. QR complex is the 80 to 120, and ST segment is the 100 to 120. Now, what is actually the arrhythmias of the ECG signals? Means what is the abnormalities occur in a system? So understood this thing that when you can consider the normal rhythm of the heart, where there is the no disease or disorder in the morphology of the ECG signal, is called the normal sinus rhythm. You know the our total heart rate of the NSI general characteristic is 60 to 100 beats per minutes. Means 72 we actually consider, but this is the normal rate. We actually consider 60 to 100 beats. If we can consider within this range, this is the normal heart rate. But for the normal heart, healthy person of the ECG comes often nearly the periodic signals with the depolarization followed by the repolarization of the equal interval. That is the normal person when you can consider all the peak. What is actually can consider the PQRST? That peak is actually the we can coming from the equal interval of the time. But any abnormality is there. You understand this thing? Is there any abnormality is there? Mean the cardiac arrhythmia is a term for any of the large or heterogeneous group of condition which there is the abnormal electrical activity of the in the heart. Means understood this thing. If the interval is actually different type of the waveform, either your amplitude is increasing, your duration of the guard peak is different, then the abnormality is actually you can got the abnormality in your system. The heartbeats may be too fast, too slow, may be regular or irregular. Arrhythmias come into the variety. So from the ECGs, from the signal point of the view, we actually understood this the your what is actually the your condition of your heart. So the what is actually the MI or myocardial infarction is the medical term used to describe the heart attack that includes the death or destruction of the heart tissue as a result of shortage of oxygen and nutrients. My MI is sometimes referred to as a heart attack because it involves the death of damage of the heart tissue caused by the lack of blood supply. Coronary artery disease, that is CAD, is the most prevalent of the lethargic diseases in which the blood flow to the heart vessel is restricted owing to the partial and the full blockage of the coronary arteries. And the coronary arteries are responsible to supply the oxygenated blood to the cardiac muscle. If there is any blockage of the coronary arteries, the heart muscle segment may be die as a result of lack of blood flow aid. So the depending of that, when this type of the MI is occur in your heart, so from the signal point of the view, we actually got. You can see that the normal signal when you can we already go through the what is the normal signal, but the abnormal signal. So this type of the signal is actually you can got from our system. So the depending of the signals previous signals, we actually what is the different of the heart diseases occur in the system, we actually divide into the this is 5 main parts we actually got. So here we actually divided the 3 parts. In the passage of the heart conduction system, there is a blockage or interruption or delay during the electrical impulse to produce a heartbeat. It is called the bundle branch block. Mainly the bundle blocks by divided into 2 class. Left bundle block means if the left side there is any blockage is there, So this is actually, you can consider the left bundle branch block, or it is not abnormality in the electrical conduction left branch or left verticals is the cardiolet system. When you consider the right side is the heart condition in which the right branch of the human heart is affected due to the some abnormality. Sometimes with the pulse rate is increase or decrease. So premature ventricular contraction is a normal heartbeat originate from the ventriculars occurs prematurely. It means that it occurs earlier than the normal heartbeat called the premature ventricular contraction (PVC). So you understand this thing. We not got the normal heart rate. When you can consider abnormality is occur, abnormality is also divided by the three. Later we actually consider four different way. Here we actually consider that these three parts. If the left side blockage, we can actually got the different type of the signals. If the right side blockage, we actually got the different type of signals. If your heartbeat rate is actually the different type of the your pulse rate, pulse is abnormality is actually occur in the high or low beat is if we occur in your system, we actually got the different pulse rate. So depending of the your biomedical depending of the our ECG signals, we actually classified the our abnormality. Okay, so that point of the view, we actually got a standard database. Understood this thing? When we actually find out that we actually working into the ECG database, real time system is not possible. So that point of the view, we actually consider the your benchmark data set, that is MIT BI1H. That is the sometimes we actually consider this database actually the MIT database, MIT DH. You can represent in this way. So the MIT database, arthritic database, we use for the our overall analysis purpose, or later we actually consider mainly the training purpose. The database contains 48 records. So each record is the 30 minutes long. The number of record used for experimentally or feature extraction algorithm is 26. The total 8500 ECG bit has been utilized for validation the system accuracy. Up to that 80% data we actually use for the training purpose, and rest of the data we actually use for the mainly for the our testing purpose. For mean the analysis purpose, we require a database, means that we require a standard database. We actually use the MIT based database in the system. So the total 8500 database we use. Out of this, 80% data, means the 680 ECG data we use for the training purpose, and 1700 ECG database we actually the classify. Now, out of this 680 ECG database, we actually later we actually discuss that this database is actually different type of the data. Is the normal data, abnormal data. Abnormal data is actually we also divide the. This is the four different classification. Mean the left side blockage, right side blockage. That is the heartbeat. Different heartbeat. So different the condition we actually take for our classification purpose. Now, what is the different methodology? How actually use for the from the raw data? How actually you can use for the classification purpose? What is the different step obtain or we can use for the classification purpose? This slide is actually visible, everybody?
Yes, sir. Visible, sir. Also moving.
So now you can see that the how actually you can use the database in the system. First, we actually from the MIT, when you can consider the MIT database, this is the actually noisy ECG signal. That is the completely raw data. From this raw data, our next step is that we actually the pre-processing stage. In the pre-processing stage, we actually denoising the our raw database. Denoising the database with different of the technique is there. So in this particular cases, we just use the multi-resonance wavelet transform, and after that your bottom line. So when you can consider baseline cases, so we actually use the removal of the baseline data. So this is nothing about the baseline. We use the filter, and we actually use the high frequency. We actually use the high frequency signal. So the mainly we use the you understood this thing. We use the three part. First, we actually got the noisy EC signal. For then we actually consider the pre-processing stage, that is the deionization stage. denoising the stage, then we actually remove our high frequency signals. After we can got remove your noise from your system, our next step is that we actually peak our ECG peak, means the R point. You can see that if we go to the ECG signals, our R point is actually the maximum peak. So second point, we actually feature extraction from our signals. So the next step is actually you can go to the feature extension. Then we actually go to our classification. Here the classification purpose, we actually consider multi-layer quality neural network. We actually consider the MPNN classification, and from that classification we actually go to the 5 different data. You can see that the normal beat, phase beat, LBB means the left block bundle block, and the right block, and the PVC beat. So you understood this thing first. Our total system, when we actually classification purpose, our first is actually can got the raw or noisy database. That data we actually pre-processing stage. Pre-processing means we actually de-noising using the multi-resonant discrete wavelet transform, and the baseline wonder removal means that we actually got the exact. We actually create our after noising, we can denoising the data. Our next step is actually we peak our R peak detection of the ECG signals. That is actually the we feature extension. You can say that this is the feature extension of the system. After we can actually go to the feature extension, that feature extension data we actually input, we take as a input data, and that is actually you can feed to our classified methods, neural network, which type of the classified you can use. So that is data you can actually put, and then we actually classified the data into the different step. Mean that we actually classified both the normal state as well as the abnormal state. So if we consider the total system, you understood this thing. If we consider this, so the first stage is the signal processing. Second step is the better extracting the feature of the increase in system efficiency. After denoising your ECG signal, so reduce the unwanted information, and denoise the signal is the most suitable to increase the system performance by providing the appropriate content which is required for the signal classification. So our next step is that denoising means we how actually can use the DWT, mean the discrete wavelet transform. So here we can see that there is the 3 different steps. First, we actually decompose the signal. We actually use the thresholding, and then we can actually reconstruct. Means the first data, your denoising signals, we actually divided into the different type of the wavelet transform. And you understand this thing, the signal function, 1 minute. You can see that from this card, the main signal we actually divided the 8 different signal type, mean the 8 different signals. So here you can see when you can consider the decouple the ECG signal. So we actually consider the different component D1 to D8. So you can understand this thing. So the 4 order DF functions with the 5 level of the decomposition. Here 5 level here mainly we actually 8 decomposition, but mainly we use the 5 decomposition, means 5 main part we actually consider D1, D2, D3, D4 and D5 was collected. Soft thresholding applied to the each level. The denoising the ECG data has been done using the multi-resolution discrete wavelet transform. The threshold values has been carefully choosing for different type of the noise to the ECG signal, and automatic threshold applied to the initial value of the noise reduction. Means that we actually threshold means actually can consider the maximum point, means the way up to the which your signal will be actually put. The 5th level wavelet decomposition, namely D1 up to the D5 was selected, and soft thresholding is applied to the each level to the decomposition from D1 to D5. Denoise ECG signal has been reconstructed again by combining the 5th level details D5 and approximately A5 coefficient for the last stage. So you understood this thing. Denoising is actually done through the discrete wavelet transform. After we actually decomposition, so our next step is actually smoothing the our signals in the bottom level. Actually, you can see that when you can go to the ECG signals, the bottom level there is the three part is there. So there is the QRS complex signals, PU wave, everything is actually can got from the bottom level. So bottom level mean the removal of the unwanted signal is very much important. So that one we actually use the baseline wonder removal. This is nothing about the one type of the filter circuit. When actually use the low component with a low frequency signal, we actually the high frequency signal we actually remove from the system. So this is the three parts we actually go through the when you can consider. First, you can see that this is the original noisy ECG signals. The second part, you can consider the number of samples with after the denoising the ECG signal, mean the after the wavelet, if the original signal you can actually flow through your system. After the wavelet decomposition, mean the after the wavelet, we actually consider that this is the B point. That is our filter ECG signals, and last is actually the baseline wonder removal ECG signal. So this is the three parts. Is you can see that from the original signal, for second point we actually consider the we put into the DWT, that is the wavelet transform, and the last point we actually consider the baseline. So this is the last part which we actually take we actually got from we use for the feature extraction techniques. So this signal we actually mainly use for the feature extraction techniques. Now how we actually can extract the features from these signals? That means actually the detection of the R peak. So after pre-processing step, that includes the denoising and smoothing and removing the baseline wonder of the ECG wave, it can be further processed to exert the useful information. You understood this thing? After raw data, we actually use the DWT, that is actually the discrete lifetime. We actually denoising the signals, smoothing the signal. We actually smoothing the signal. We actually go through the removing the baseline wonder. Mean that this is nothing about the one type of the filter, that is actually a high frequency signal. And next our work is actually we extract the features. So the extract the features means what I understood actually this thing, that we are already go through the ECG signal. There is a 5 peak is there, or the 5 waveform, or you can 5 different point we actually mainly peak. So that these 5 the ECG signal morphology includes the 5 main peaks, that is from P peaks to the T peaks. You understood this thing, that if you go to the total signals, there is a 5 peak is there. So if we consider the 5 peaks, means you can see that from here you can see that this is the P wave, P, Q, R, S, T. So these 5 peak we actually mainly consider about this is the 5 different peak we actually mainly extract from our signal. So you understood this thing. The ECG signal morphology include the 5 main peaks from P peaks to the T peaks, where the QRS peaks are called the QRS complex, which contain the maximum information for the cardiac function. Mean that if we go through that means if we go through the higher peaks, so we actually in the surrounding we actually already got for what is the QRS piece or the QRS complex. So our aim is that how actually we can extract the from the signals, mean for the ECG signals, how actually you can peak the R peak in the system. So R peak is the highest peak in the ECG waveform, and it is generally in the center, and it is also the energy of the QRS complex is surrounding around this peak. So the first and foremost requirement to detect the R peak, based on which the QRS complex will be extracted. So in this work, MRDWT in the C-set wavelet has been used for the R peak detection. Now, what is the different algorithm we use? So that is actually you can explain here. So you understood this thing. Feature extraction algorithm we actually develop. This is the what is the step by step how actually can peak our R. So first is actually denoise and the smoothing the ECG signal is considered. means the smooth ECG signal we can consider. Then second is the decomposed the signal using the multi-resolution discrete wavelet up to the 8 level wavelet function used to the decomposition in the 6th order decomposition function. The third, fourth, and the fifth level of detail coefficient are selected. Out of the 8, we actually use for the third, fourth, and the fifth level of the coefficient. Selected the extraction of the QR section. Since the D3 and D4 consist of the maximum information of the energy spectrum, here the D3, D4, and D5 are detailed coefficient of the wavelet. So we actually, out of 8, we actually mainly considered of these 3, 4th, and 5th. Why we actually consider the 3, 4th, and 5th? So that is also written here because this is the maximum energy spectrum of the system. So after the next step is actually you can calculate the total energy. We actually find out the X. X is actually we can find out the D3 plus D4 by D5. And the new function Y is actually defined in the D3 into D4 plus D5 divided by 2 to the power n, when n represents the level of decomposition. Mean the which level of decomposition you can actually consider. So that is actually used for the n. The next step is actually the Z. That is actually our objective function. The optimizer technique ensure the value of the Z is maximum. So the value of Z is actually calculated. You can see that the Z is equal to X into Y. So X into Y means X we actually find out the X and Y both are we actually find from the our decomposition function. You can the level of the system. So D3, D4, and D5. After that we can find out the X and Y, and from that we actually find out the Z. Our main aim is that we actually find out the maximize. Actually, why we actually consider this is not the minimize optimization. We can find out the maximize of the Z, because our main aim is that we actually find out the R peak. What is the maximum peak is occurred in your system. So this technique is adapted because automatically detects the maximum amplitude for any real time or stored ECG signal. Now the maximum amplitude point is labeled as R, that is the Z max. R is the initialize, and determine it. Now we actually find out the determine the Z. You can understand this thing. We actually go through the, after we can find out the Z. Now we actually find out the feature extension. Z is actually you can consider Z max. Understood this thing. If we find out the Z max, we actually find out the what a maximum peak is occur. After that, we can find out the maximum peak. We actually divide the signals into the two different ways. Mean the R is equal to minus 50 and plus 50. So we actually find out the minimum and maximum duration of the Z. Mean the what is the maximum Z? Mean the R peak is occurred in your system. So you can starting from the, we actually go through the 50 means the total 100 points we actually find out the board. Out of these 100 points, we actually extract that 20 features from the system. So again, I repeat, first we actually the signal is actually the 8th level signal we decompose. Out of this signal, we actually mainly consider the 3 parts, D3, D4, and D5. From that, we actually find out the total energy X and Y. From the optimized function, we actually find out the Z is equal to X into Y. Out of this, we actually find out the maximum peak, that is the Z maximum. That from that we actually find out the what is the maximum R is occurred in a system, and out of that we actually, after we can actually calculate the Z maximum value, that is the R peak. From that we actually find out the minus 50 and plus 50 maximum and the minimum duration of the system. So after that we actually find out that this system we actually find out the 21 features point. So that is the P1 to P21 we actually find out. What you understood this thing, if we go through the step by step, so that we better understood that this is actually the algorithm how actually we use this is the flow chart. So first we actually understood this thing, de-ionizing the system is the signal. Next stage is the decomposition of the 8th level. Then we actually use the find out the X and Y. Out of this 8th level, we actually find out the only D3, D4, and D5. Then we find out the X, Y. We find out the Z. From that Z, we actually find out the what is the maximum amplitude. After that maximum amplitude, we actually find out the what is the Z value, and this Z we actually divided by two part. One is actually the minus 50, Z equal to R minus 50, R plus 50, mean the total 100 sample we use. From the 100 sample, we actually find out the 20 special features from the your system. So these 21 point features of the signal. These 21 point we actually mainly input to the our classification process. So here we see that the how we actually decompose ECG signals. What actually you can go to the theory parts. What actual cases how actually can go to this thing. First one, you can see that the red one, that is our original signal. That is our mean the smooth signal denoising signals in the system. Out of this signal noising signal, we actually consider the 8 different decomposition, A1 to A8. And here we actually consider you understood this thing. This is the 8 level function, wavelet function. We actually consider D1, D2, D3, D4, D5, D6, D7, D8. This is actually the we can consider different coefficients. So mainly the energy signal we actually you can see that we actually use the D3 to D6. So after that we D3, D4 and D5 coefficient. D3, D4 and D5 coefficients are identified by detection of the QR complex. So here we actually you see that we actually mainly consider about these three signal. The coefficient level of the 3, 4, 5 so the better with the QRS complex, or all other appearing to the noisy with respect to the QRS origin. So the next you can see that how this detailed coefficient of this system how actually plot mean the when you can consider the X into Y coefficient. So this is the D3, D4 and D5 signals. Out of these signals, we actually find out that these energy signals, and these for energy signal we actually optimize the signals, and we actually find out what is your R peak. So that this is the identifier of the R peak. You understand this thing? These signals when you can consider that this is our after that this jet max, we find out that this is actually the detect the R peak from the system. So you understood this thing. So from this is actually our signals. From there we actually got the 21 features point. So how actually got the 21? This is the extra the feature of the ECG signals. 21 features point we actually consider for the total signals. You understand the 100 samples when you can consider the 100 points. Depending of that 100 point, the 21 features point we actually got from the signal. So that is actually first from the peak from the R peak. So that is the Z maximum. From this Z max, we actually got to the 100 samples point, and from these 100 sample points, we actually extract the 21 features point. So this is the extract features of the ECG signal. So if we go through the RAP wise, you understood this thing. First, we actually got the raw data. From this raw data to the wavelet transform, we actually the denoising the signals. In the baseline purpose, we actually use the filter circuit. After we actually denoise the filter circuit, the next step is that our main aim is that we actually find out the R peak. So similarly the 8 decomposition from the wavelet transform. So we actually find out our energy signal, and from this energy part, we actually find out what is the maximum peak, Z maximum. For this Z, we actually find out from this Z, we actually find out what is the R peak. From this R peak, we actually take the 100 sample, mean the plus minus R is equal to you see that we can consider the R is equal to minus 50. R is equal to minus 50, R is equal to plus 50. That is the minimum and the maximum duration of the Z. And from this point of the Z1, we actually got the 21 features point. So this is the different features point we actually got in the signal. So if we got the different of the features points, we actually see that depending of your ECG signals, we actually got that this is the 5 classified signal from the system. 5 classified signal means if the normal signal is there, so we actually got this type of the different of the signals. If we consider the left block, so you can see that there is some definition. So this is actually the already the existing signal is there. So from that we actually classified. So that is actually the LBB signal is there. After that you can see that that is the your red side block. D side when you can consider the PVC signals and the phase speed. So this is the 5 different classified signal you can got from to the analysis feature extraction techniques. So understood this thing. This is the our input signal to the our classified. Which type of the classified signal you use? If you use the neural network, you can use the classified. So that is the your input signal. If you consider deep learning, that is also your this is so first we actually create the input signal from the wavelet transform as well as the decomposition method. So this is our input to the your system. Now after the classified the signal, we actually find out the error matrix. Now what is actually the error matrix? So understood this thing, after you can classify it, we actually find out the what is classified, that is your system is correct or what is actually the which percentage of the signals is you can correctly classify to the system. So the what is the actual classification outcome? So that one we actually use for the confusion matrix. So that is actually nothing about, we actually consider the, we actually find out the how much error in your signal. So here you can see that there is the 4 block is there. 2 positive bit, 2 negative bit, false positive bit, and the false. So 1 and 4 is give the your exact signal. What is the exact signal means? 2 positive bit means if the your signal is abnormal and you after the classification, if your this signal is detected to the abnormal, that is means that this is the 2 positive bit. 2 negative bits means if the your ECG bit is normal, after classified the if the your signal is actually coming to the normal, so that is actually considered the 2 negative bit. False positive bits means if the your normal class, if the detect is the abnormal, so that is called the false positive bit, and the false negative bit is actually the abnormal ECG bit detects as the normal. So that means the which percentage of the your signal when you can classify it, what is the your percentage of the signal you can classify it properly classified, that is actually that data we actually got from the confusion matrix. So this is you can understood this thing. This is the different assessment measures values. This is a totally statistical analysis. We actually consider the so this is the different type of the assessment measured value is there. So we actually find out the classification assessment matrix. So this is actually considered accuracy, classification of the error rate, specification sensitivity, positive predictivity, F score, and overall accuracy. So understood this thing. When you can find out the overall accuracy means you understand this thing. We actually find out that total positive bit means that you understood this thing. What is actually you can classify total positive bit, total negative bit. So that means this one is the total positive bit plus total negative bits divided by the your total signals, divided by the your total signal, that is actually give the overall accuracy. Means that if the your signal is you can properly, your accuracy is very high. If the overall accuracy is actually given, the percentage of accuracy is high, means you can actually well predict it, well classify the signals. Means the actual signal you can got from the your classification. But the what is the error rate? So error rate is actually the, if this rate is very increasing, that means the error is classification error is there. So you can again classify the your system. So the you can properly classify the your system you can got from this measurement. So the classification error rate is given the false positive bit plus the false negative bit divided by the total bit, means the total classification bit in the system. Understood this thing? This is the means of 4 bit. We actually total classification we divided the 4 part. If the 4 part is the number of false bit is increasing, that means the your error rate is very high. If the overall accuracy, if the 2 bit is increasing, that means that your accuracy is very high. Sensitivity means if that 2 positive bit divided by 2 positive bit plus the false positive bit. This is the sensitivity in the system. So our mainly aim is that we actually increase the overall accuracy in our system. So after the classification, your confusion matrix is actually give the data so that you can properly classify your system or not. If you not properly classified the system, you can reclassify it. Otherwise, you cannot properly prediction the system. So because this feature extension data is actually can input to your classified techniques or the input to your neural network. So that one of the proper classification is required. So the next step is actually the neural network. I not go to the neural networks because you can see that everybody knows. So there is the three part is there. So the input part, hidden part, and the last part is actually that you can consider the input layer, you can hidden layer, and the output layer, and the input to the output layer, the weight matrix is connected. So when you can consider the use the neural network classification, we actually mainly update your weight matrix. So in this particular cases, in this particular problem, we actually use the multi-layer probabilistic neural network. So the multi-layer probabilistic neural network is classified the fast processing time and the good accuracy. And NP is the type of the feed-forward neural classifier having the 4 layers, input pattern, summation, and the output is also called the multi-layer feed-forward neural classifier. Okay, the probability of the each new class estimate the determining the PDF the each class and the final class allocated depending on the maximum of the probability of the bias rules. So the what is actually the structure of the probability neural network? So the same time you can see that the 21 features we actually consider as the input data. So that this is the input layer. So that is the 21 features we actually consider. Between the input and the output layer, you can see that there is the petal layer is there. So this is the hidden layer we actually use. And the output layer, we actually use the 5 different classifier. 5 is actually, you understood this thing. Here the 5 classifier is the normal, abnormal data. Abnormal data we actually consider 4 data. That is actually the PVC, the left blockage, right blockage. We actually use the left blockage, right blockage, as well as we use the PVC. That is we use the premature ventilation. So 5 data set we actually predicted. Now, how this is this is we use first we understood this thing after the feature extension. So that feature extension 21 data we actually input to our neural network, and from this 21 data set from the features we actually predict the 5 different outputs. So output is actually our which type of the particular what is actually feature extract data, what is the which domain mean after we can actually feature classification which domain mean what is actually classified, this is normal data or abnormal data. So that is actually you predict to our neural network. So neural network we actually use for the prediction purposes here. So understood this thing again a bit. We actually mainly use for the MIT based database. Out of this database, you can see that the 8500 ECG database we actually use. Out of 80% data we actually use for the testing purpose, and remaining data we actually use for our testing purpose. So 170 bits are used for the testing and detection purpose, and MIT database is used for assessment and classification purpose. So when you choosing the 500 bits, when you choosing the database, 1700 bits are used for the testing. You understood this thing? How actually can choosing the data? When you can use the testing data, 500 bits data we actually consider normal data bits. We when you can testing purpose, we not use the arbitrary data. We have 500 bits data we actually consider the normal data. 300 bits are used for the PVC. 300 bits or the LBB when the left branch bundle block. Okay, 300 bits of the pace ECG and 300 bits mean the 5 different classified data we actually use for the testing purpose. After we can train the networks, but testing purpose we actually use this out of 8500 6800 we use for the training purpose, and remaining 1700 data we use for testing purpose. This testing data we actually divided in this way. 500 bits is the normal, 300 bits for the PVC, that is actually the use the premature ventricular contraction. 300 bits for the mean the abnormality, only the 500 bits normal, remaining 1200 data we actually abnormal data we actually use for this thing. So we actually find out the accuracy, mean the what is the accuracy rate we actually find out the use of the MME classifier. After we classified, that data is actually compared to the existing data set. So you can see that so this is the different data set we actually mean the compare. This is the 4 existing data set we actually backwards and neural network, multi-layer perceptrons, and the suppose vector machine. So you can see that the results, when you can see that the results, so out of this 500 data we actually consider the normal database. This is the testing purpose we actually consider. The your accuracy is actually the coming the 97.95 when you can consider the backwards and same data set we actually use. So here we can actually the total number of classified here, the 5 bits we actually consider the normal, pace, LVB, RVB, and the PVC. Out of that, we actually consider the what is the different phenomena. I mean the how actually you can classify it of the error, what is the percentage error, how actually you can consider percentage score. Out of this thing we actually find out the 97.94% classification is possible to the your backwards and neural network. But when you can consider the multi-layer perceptrons, so this that is actually 98.53. When you can consider the support vector machine, so this is the 99 percentage. And when you can consider the MPNL, that is the what is the existing we can use, that is actually the we use the 99.53. So that is the all the 5 sets of the normal to the piece of the normal as the abnormal cases. We actually their prediction is actually very accurate. Now, what is so we can, if we go to the summary of this system, mean the total presentation. So 1700 ECG bit we used, tested, and classified into the 5 classes, 5 types of the arthemize. That is the abnormality we use, that PVC, RVB, paste, and the LVB and the normal bits can be detected. We utilize the 21 feature points as the input, and 1700 ECG bits for the 5 different class are tested using the your MPPN. The overall accuracy and percentage achieved using the MPN is excellent, with the 99.53 accuracy is actually got from the system. The accuracy as a percentage of the BPN in the 97.95, 98.53, and 99. Etc. Now, what is the limitation of the this type of the system? Here you can see that the very small data set we actually mainly use. Only the 8500 feature set is actually if you use the large set, your system will be failed when you can use the conventional neural network. The traditional machine learning classified has been utilized as optimized detection, which may not be performed well in the large data set. The system accuracy mainly depends on the feature extraction methods. To overcome this issue, we actually mainly the hybrid deep learning model is proposed, and the large database can be considered for the training purpose. When you can consider the machine large database, you use hybrid deep learning methods. So we actually also look after the misbalancing problem is also. I not go through the deep learning method, but how actually I just give the overview of the how actually you can go through the deep learning methods. Mean the what is the step, what is actually the previous step we actually consider, what is actually the deep learning, what is actually not previous cases, and what is the main difference between these two. You can see that the previous cases, when you can consider normal neural networks, we use the input feature extraction, then we actually consider the classified, and then we actually got the output class. But when you can consider deep learning methods, the feature extraction and the classified is occurred from the itself from the deep learning system. You understood this thing? So this is the very your feature here. The mainly task if your feature extension is not good, you can actually not, because the your from the feature extension you actually input the your classified data. In the deep learning methods, so this is directly you can from the input what is your raw data. So this raw data is actually from this raw data is the deep learning methods, we actually the feature extension as well as the classification purpose. So the main aim is when you can use the deep learning methods, so you can either you can use the CNN or database balancing techniques. So this is all about the today. Anybody any question? Hello?
Any questions? Please, you may ask. Any question? Please, you may ask from the sir. No question? Okay. So I'm going to conclude the session. Thank you so much, sir, for taking the time to share your expertise with us. Your presentation on detecting deadly disease using biological signals was quite beneficial. You informed us how ECG signal recording is done by catching. You provided us with a brief descriptions of wave segments and intervals as well as time durations and amplitude. You mentioned arrhythmia in ECG signals and abnormal heartbeat activity, knowledge of bundle branch blocks and their various varieties, including left, right, and premature bundle branch blocks. The MIT BIH Athenia's database directory of ECG signal is used with 80% of data used for training the model. You clearly describe how raw data is used for classification using the proposed methodology, which includes the raw database, the pre-processing state, R peak detection of ECG signals, and so on. Provide us with a detailed descriptions of each phase using an interactive flow chart and graphs. Explanation of feature instruction. The algorithm works in stages using a decomposition function and an optimization mechanism. Where is neural network, deep learning utilized, and how is it implemented? What is the precision of the data and the limitation? So once again, thank you for making a contribution in this STC. Thank you
Okay,
so much.
thank you. Oh, really.
Okay, you all may leave it by tomorrow. You may join 2 o'clock before 15 minutes, 1:45. So please join by tomorrow 1:45. Thank you everyone. Okay, you all may leave it. Thank you so much. Please by tomorrow just 1:45 join. Once again. Thank you.
Okay, sir.